Okay, so my talk is about type safety, or specifically why types are not safe. So let's get started. And I can't see my notes because connection issues, so we'll hope things work out okay. So for the last about 10 years or so, I've been chasing correctness in some form. And I didn't know that that's what I was doing when I started. But that seems to be the case. I've been chasing correctness in some form. This led me to Haskell and type systems and these types of things. And I've had some experiences in that time trying to chase correctness in my own way that led to some sort of surprising outcomes. For me, at least, the most surprising was to realize that types themselves are actually not safe. So what are types? Hope this is going to be a little bit interactive. Everyone here is familiar with types? Okay. So I'm going to give a very, very basic conception of types. That types are sets with a predicate, right? We are starting with the universe of all things. We're going to filter down to something smaller than that. And types are also not about computers. Everyone familiar with that types are not actually about computers? Okay, no responses. All right, so they're not about computers. They're actually an abstract concept. And in reality, they're quite dangerous. As you can see here, some types attacking some people. We've all experienced the dangers of typing ourselves, of course, as programmers. But let's say the number 5. The number 5 has more than one type in reality, right? In fact, it has many, many, many types, as everything does. So it's a real number, right? It's also a rational number. It's a natural number. It's an integer. It's an odd number. And it has all of these types at the same time. In a computer, typically, you wouldn't model it this way. You would say my 5 has a single type. And the reason for this is that at runtime, it has some features. It's either 32 bits or something. And so we don't want to get these things confused. But in reality, we can just look at it this way. But it's not just numbers. So we've got, for example, Dagos. He's real. He seems rational to me. I don't think he's juicing. He can be pretty lax. He's strong. And he might be monoidal. So what's the point? What's the point of types? So when we're talking about type systems in computers, typically there are 4 things that we get, okay? Or 4 things we actually get from the presence of types. One is the prevention of errors. This has to do with correctness, right? The second one is metaprogramming. You guys are familiar with this, but metaprogramming and types are very closely intertwined. There's optimizations, like from the compiler, and ergonomics for the developer. Right? We want to be able to communicate and understand what's happening in this code via the types. Okay. So we have another question here, which is when do we check? Right? So so we're going to come back to ergonomics. We're not going to cover optimizations. We are going to do the others, but we're going to start with preventing errors because that was, at least for me, my motivator behind engaging with types. Because I did not want so many errors in my program. And that comes to the question of when do we check? Right? So I'm going to make an assertion that type systems are fundamentally about processes that run for a period of time when it comes to error prevention, right? So one way this can be stated is that Nix, you guys all familiar with Nix to some degree? I would say that Nix has the finest type system today of almost any programming language. It is reality typed. Fair? This is because it is a build time language, which means anything that goes wrong that's a type error is in fact checked because it is a build time language. So when we check matters. If we are only building something once, there's no purpose in having a type system for error prevention because we will get the error right away, right? We really use the type system to prevent errors later. And so there's kind of a fuzzy definition of what later means, right? When is later? Is it later today? Are we doing maybe machine learning where it's going to be a very, very long training process and we don't want to reach an error a few hours in? Is this a web application that's supposed to stand up for months and months and months and we don't want it to crash? Right? So when is later is actually not well defined. But I'm going to say later is anything where we do not know when we're going to be stopping the program. It does not have a known termination point. Okay? So anything that does not have a known termination point already has the greatest type system you can possibly imagine because it is reality typed. It is empirically typed. The fact that it built it all means that it worked, right? So when we're talking about using type systems to deal with defects, to deal with errors, There's actually kind of a bunch of people doing taxonomies of software defects. This is kind of my fuzzy blob of different types of software defects. We can have performance defect. Is that addressed with types? No, it's not. How about scalability defect? No. Race condition? Maybe. Sometimes. Functional error? Same, maybe, sometimes, that's right. Configuration? Maybe. Could be. Usability? Definitely not, right? You can find a type system that will tell me that the button isn't colorblind approved, and now someone can't figure out what the buttons are saying in the UI, I'll be very impressed with you. Well, actually, so to be fair, there's sort of an argument there I'll make later for a potential use case for AI. But anyway, logic errors, definitely. A lot of those can be stopped with types. Product errors, product defects. Product defects are defects in the design of the product itself. It wasn't a good market fit. It didn't actually help the user very much, right? None of it. So the reality is that if we're talking about types, and this is LambdaConf, a lot of us have kind of a almost spiritual sacrosanct obsession with types, right? This is intended originally for most of us because we want correctness. But if we take a look at the taxonomy of actual software defects that are seen in the real world, most of them can't be addressed with types. And the ones that are definitely type errors represent less than 5% of defects. That's what the empirical evidence suggests. So we are putting forth a tremendous amount of effort and time into doing type-level, type system things that at best eliminate maybe 5% of errors. All right? And then we want to validate, right? We want to do, like, what means do we have of stopping these errors? Types is one of them, right? We put dependent types up there. But there's a ton of stuff, right? Functional testing. I think I missed an L there. It's supposed to be bundling. External validation, right? These things aren't really types. There's kind of a lot of means of validation, and yet we are kind of very, very disciplined, focused on one thing. And if we take that to sort of its logical extreme with dependent types, have any of you worked with dependent types? Okay. Are you still thinking? Have you not burnt out all your synapses with pain proving to the compiler things you know damn well are correct? Okay. If you've done that, I genuinely respect you because I can't. At some point, I'm just lost. Okay. So correctness, I want to give a definition of this because we don't seem to have one. Right? When we say correct, we all kind of go, okay, this is what the spec was, and did it do it? Is that correct? When it comes down to it, correctness is about expectations. Whose expectations define correctness? Is it the engineer who's written the code and written the tests? Is it the product designer who designed the product, or the business person? Is it the user who's using the tool? Right? It's about expectations. Correctness is fundamentally fuzzy. So we're using a highly precise tool to eliminate a small class of errors at great cost and effort in order to enforce something that we don't even know what it is. Okay? There is no source of truth for correctness. Period. Nobody is going to be the one person who can be the source of truth for how a user, product manager, programmer, whoever it is that we're talking about, is expecting the program to work. And that's all correctness is. We don't like surprises. That's ultimately what this comes down to. We don't want to be surprised because we got woken up at 1 o'clock in the morning because the server went down. Right? But how much is that really worth? If you think about this in terms of objective ROI, being woken up at 1 o'clock in the morning because the server went down, how much did that cost you? How much did that actually cost you and your organization and your business? Versus what would it actually take to prove that that's not possible in a dependent type? Just want to throw that out there as a suggestion. All right. If you think that you're, so this is what it comes down to. I think that correctness and type system, these things are ultimately fake news. It does not deliver what it's promised. It delivers something cool, but it does not provide the soundness and guarantees that we would hope for, specifically because we're only enforcing that our expectations as engineers are met, and that is not a good definition of correctness, and this only eliminates a small class of bugs at potentially tremendous amounts of effort on our part, which is expensive. we charge people a lot of money to prove that things will not fail when we already know that they won't. Okay? So let's talk about actually using types. So a lot of people can argue that if you're having a bad time with types, you might be misusing them, for example. Right? But what if you're actually doing type-level programming? Can we do better than this? No, we can't. And this is because at the top level, all things are typed type. Right? The type system itself represents a programming language that is untypable. As in, the type system itself is a programming language in which you can have errors, you can have problems, and there is no way necessarily to use types to prevent those because the type system itself only has type. So, we think we're being more clever than this. We're not. All right, so so I'm going to get into some concrete examples. You guys familiar with void? All right. So void is an uninhabited type, right? And this is kind of where types are fundamentally weird compared to the real world. You're allowed to have things with no correspondence to reality whatsoever. And this is an example, void. Void is an uninhabited type. There's nothing in there, right? And so is this a problem? Is this producing issues in the type safety of the type system? Here's another encoding of void that I'm fond of, I wanted to share, which you can do in less advanced type systems. If you want void and you're in a type system that doesn't have the ability to just declare it like that, making an infinitely recursive type is still unconstructable, so it's still essentially uninhabited. It's void. Right? My engineer Mason McAman thinks void is sick. And while there are use cases for uninhabited types, there's only one that I'm actually aware of. I'm going to show you what that is, just to caveat why, before I go into why uninhabited types are so bad. This is the use case for void. I'll give you guys a second to take that in. Okay? Do we get why this is a good use case for void? It never returns. That's right. This is a non-terminating function. This will go on forever, endlessly printing out one more A to annoy the user. Okay? And we could make that generic. We could just say void A. Right? And the type system would accept that because it doesn't return anything. It'll never terminate. So this is a place where you could put string there, you could put int there, you could put unit there. The compiler will accept it no matter what, and it's all a lie. Right? It's not returning. This I/O doesn't return. The only kind of reasonable thing I think to put there is void, which correctly sort of documents that this doesn't return. It shows you that it's not there. And then, for example, if you were to have a bunch of these, if you read FP Complete has an article on this where they use race across multiple threads, and then they show, hey, look, we can use void to go, well, this thread we know doesn't terminate, so we get the answer back from the other thread. We just want that. We want it in a type-safe way. So this is the one use case for it that I can see. All right. But Haskell, for example, will accept code like this. Is there aware here? There is no F. We actually have an entire function here. We have term-level logic going on, but there is nothing that will satisfy F. There is nothing that is both covariant and contravariant functor. This is nonsense. You can't be in both positive and negative position at the same time. If you have something that is both in positive and negative position at the same time, you have an invariant functor, and that means that you need a function from A to B and B to A simultaneously. To have a covariant and contravariant functor at the same time is impossible. This code compiles. Why does this code compile? It compiles because types are allowed to be uninhabited. And the compiler is not smart enough to figure out that just because types are allowed to be uninhabited, you're a programmer and you probably don't want that. You probably want this code to execute at some point, and it's not going to help you. All right, here's another example. I want you to tell me whether or not you think this code should compile. Is there anyone who thinks, yes, this code should compile?
Can you explain what the code does?
With the what?
Can you explain the code, what it does? Like, I'm not familiar with it.
Oh, okay. So if you guys are not familiar with Haskell, I'll explain. So, excuse me. I should have used code defunds. This is the problem. All right, so we can't see it now. There. It just needs to be wiggled, apparently. All right, so here we have colon, which is type of, right? So bar has a type of. And then we have a constraint between the parentheses and the actual type of what we're returning here, which is just unit. So bar is unit, but we have an ambiguous type X that has to be satisfied before we can use bar for anything. And the ambiguous type X has to be both true and false simultaneously. All right? So true and false simultaneously. I think I have another encoding of this. That's nice. Yeah, whatever. This is another encoding from my friend Sid. Gave me this one. So this is another example. Both of these have the same sort of property, right? We have an impossible condition. His is a little bit different. Mine actually is unit. His returns bool. But you can see whatever is actually equal to unit. I want to know, does anyone here think that either of these should compile? The second one could compile? The character is not an integer. It may be at runtime, but it's substantially different type-wise. But regardless, if I do an if statement on whatever, it's a bool. But it's equal to unit. Is that cool? Seriously, does anyone here think this should compile? Wrong. This should absolutely compile. And it should absolutely compile because types don't have to be inhabited. X doesn't need to exist for this to be a valid type. And the second one should compile, even though types doesn't require the uninhabitability of types, because if you think about this in terms of logical implication, if int is char, which it's not, then unit is a bool. Because any statement followed by a falsehood is automatically true. So both of these are fine. Not what you want as a programmer, though. Right? I see this in the code, and we're going to talk about where this actually reports. Where do you think this error is? How is this error going to report? So this one, actually, believe it or not, this one does not compile, even though it should. And this one does compile, even though I would argue it shouldn't. But at least the top one isn't callable. So it will never be a runtime error. So neither one of these introduce runtime errors. All right. So how bad does this kind of problem get? And so I'm going to go into kind of a concrete example that was inspired by the lovely error messages of Servant. Who here has seen the error messages of Servant? I'm sorry. All right. So Servant is based on a concept called type class induction. Okay? Type class induction is the notion that if we have a type, we can have a series of type classes polymorphically traverse that type at compile time in order to construct a something. Right? In the case of Servant, we have a type that represents an API. We traverse that at compile time using type classes inductively in order to produce a something. A client, for example, for that API, or a server. Right? Those are the two most common. But you can actually do whatever you want with that. You could do an open API spec, and you could also make it do poetry if you wanted. All right. So here's a very simple, I'm going to do a type class induction for you and show you how this gets out of hand. So here we've got a data type expression. Okay? It's a very, very simple little expression syntax. We've got plus, we've got multiply, and we've got v, which represents a value within the expression, right? Okay, we good on this? All right. So here is a simple type class induction. This is a simple type class induction that will print out the expression, right? Because our expression is a type. It doesn't have a term. There's no value level representation of it. And it can't be because its kind isn't type. Right, its kind is expression. But here, we can go through it. So we make a type class, print expression, which is just a string, and it takes E. So it is ambiguously typed. We're going to use type applications to resolve the type ambiguity in the compiler so that it knows what to pick. Next one there is printing for V. And all we do is we use known nat to get the type value out of compilation into a term. So if that's a number 2, nat value will be the number 2. We turn to a string with show. Very simple, right? Same thing with multiplication. You kind of see what's going on there. And same thing with addition. So we're iterating through this thing, through the constructors of expression, in order to print out a string representing that type. Okay? So that's nice. Nice, right? No. Come on. It's trying hard, man. All right. Something's bouncing. All right, so here's I'll just stand still. I'll try and be still. So here's another induction for the same expression. So this one will actually evaluate the expression and give you the result, right? So same thing, we're iterating through it. We have the same basic constructor setup, and we get the result. This is what, this is more or less the technique being used by servant, right? So we have a type class and servant has server. We give it the type, and we get back our server, right? Has client, the type, we get back our client. So this is a nice thing because we can interpret it two different ways, right? Except, so let's see if I can do this without looking. What happens when we get an error in here? Right, so I'll go ahead and run this. All right, so we get it back, right? But where is the error going to report if I introduce a problem, let's say, here? All right, that one, I believe, will report in the right place. Yeah, it'll show us show. What if, alternatively, let's do something else. So that's a little expression foo there that we're evaluating. And so we see how far away from the actual location of the error we get our error reporting. Right? It's going to report the error at the point of type evaluation. This is, in this case, it's pretty darn minor. We can figure it out. It's very small. But if you have, for example, 4 or 5 or 6 type class inductions barfing into one another, you're going to get an error at the bottom of that at the term level that says, hey, somewhere inside of this giant type class hierarchy, something didn't work, and guess what probably didn't work there because there's nothing to do? It's going to be something like this. Right? Another example is vinyl. Have any of you guys used vinyl in Haskell? No? So vinyl is a library for extensible records, and you can do things like say, X is a member of this record. You can also have a constraint that says X is not a member of this record. And sometimes doing that made the code compile, and it's very not obvious that your constraints contain an incoherent concept, particularly to notice that when you've got a constraint list like this, and the error is being reported over there. Okay? All right. Additionally, for this one, we could have done it at the term level. That's the whole thing without the type class induction. Right? There was no need for a type class induction in my example, and I want to be clear about why as well. If you don't need type class induction, definitely don't. And you know that you won't when you can simply have the values. Right? Part of the reason you need this for something like servant is that the handlers are themselves typed. So we can't do it at the term level. You can't make a record. I mean, you can make a record of type reps or something and use typable. Maybe there's some magic you could do, but it would be nasty. Servant is actually fairly elegant. Okay. Okay, same thing. Get the same result using entirely term level. There you go. The iframe kind of captures the mouse. Additionally, in most systems, there's no, 5 minutes left? All right, I'm trying. There's no type level pattern matching, at least in Haskell. So if you have, for example, a desire to have a type class instance that says, and you want to say, I want to use this instance when this constraint is satisfied, and when it's not satisfied, use this other one, you're screwed. They both have the same level of polymorphism. So if we have an A that is an instance of monoid, and we have an A that's not, the A that is instance of monoid automatically matches both type classes. Right? And so we don't actually have the ability to select the order of execution in the compiler as well. Can you imagine how you would cope with that on the term level? You can do pattern matches and these things, but you can't actually choose the order. All right. So I'm going to take a detour on cardinality, but I'm out of time. Are you guys familiar with cardinality as a concept? Okay. So any given type has a cardinality as the number of inhabitants. And there's also the question of honesty in types. Right? If we are going to be saying that types are for correctness, and correctness is about expectations, then it's very important that our types honestly communicate our intentions, right? And that's generally not possible. But I would argue, at least briefly, I won't go into my argument, but for your types to be honest, the cardinality of your type must match the image of its execution within your program. Any cardinality beyond that is dishonest. You're saying, I'm going to give you something, maybe. I'm going to give you something that I will never give you, right? Or I will take something in here that is far more than I need. So we need to be honest with our types as well. Here's an example of something we can't catch. So this is a servant endpoint. Can you guys see why this is wrong? Okay, it is a correct type. It is type safe. It will compile. It will do all the things. We just promised you a JSON encodable data structure of no content. This is real no content. The server is going to send nothing, but it's going to give you a 200 and with a MIME type saying it's JSON.
Well, it's nothing. Can you prove it wasn't JSON?
No, I mean literally it sends no bytes.
I know.
Yeah.
But those bytes could be JSON.
No bytes is not JSON decodable. I tried this. I ran into this. This took me hours to figure out what the heck was going on, and then I found out that there's a combinator servant called getNoContent, which actually does this correctly and returns 405 instead of 200. And not 405. What is it? The no content one, whatever that is. Anyway, we also have other cases like type CSS. Type CSS sucks. The correctness of whether or not your CSS is right is, did it look right to me? Right? It's a style sheet. Never, ever, ever has an engineer had a problem at runtime because they used an int where there should have been a string in their CSS. We don't need this. It doesn't help with that. It's about what are we validating. What's correctness means? About expectations. An expectation with CSS is that it looks not broken. And not good for types. We try to do that with types. And there's other things we can validate. So here's something to note. W3C has an HTML validator. The HTML validator is so complicated that to represent that as a type system requires dependent types and quantitative dependent types and linear types in order to do what this validator does on HTML in a few seconds, right? There's a reason this wasn't written as a type system feature, right? It was written as a validator because type systems aren't good enough for that. Yeah, please do hire me. I'll finish up though. So, there's just other things we can do for validation that aren't types. I find a personal embarrassment to be that dependently typed languages almost all have linters. You see my point? All right. So that's it. I just want to kind of break people free from the religious sort of idolatry of type systems that are going to give us correctness and suggest that maybe we should have a little bit of faith in ourselves. Sometimes we know it's going to operate properly, having this level of machine-checked proof, we're way past the point of diminishing returns as far as I'm concerned. And so if you're looking for pragmatic help with Haskell, Nix, or Rust, or these other types of things, please do hire me. I am available. And that's it.
So, of course, my first thing that I feel like I want to say is, preach it, hallelujah, amen. And I've obviously got my idea of the alternatives for this, but do you have a vision for what an alternative future that spends less resources on formalized type safety and more resources on something else to approach practical correctness at, say, problem scale or application scale?
The two things that actually would help here, in my opinion, are less types, right? As in, we are not capable of doing what we want to do with types. So we limit our expectations of types. We temper how far we're going to go into teaching the type system at our program. And instead, tests, validators, right? Things like linters are actually really good. Yeah, unit tests, validators are really good. I think that for things like UI, it would actually be worth it to develop an AI that has a reasonable understanding of looks broken. We can find ways to validate these things outside of types that are, frankly, a bit better. If you have a CI system, you can get performance metrics out of that. I know a lot of companies don't test the performance of their code in CI at all. A lot of times because they're spending all of their time trying to convince the compiler that the basic facts of their program are true that they know is damn well true, right? write Lisp, right? And if you write untyped code, you can write correct code. You just have to have slightly more faith in yourself. Have slightly more faith in yourself. This is my message from this talk. Types are cool, just don't make it your whole identity, man. That's where I'm coming from.
So why haven't we invested enough money into types to make them strong enough to represent everything we need?
Because you can't. You fundamentally can't, because uninhabitable types are allowed, unrepresentable types are allowed. The nature of types and type theory itself is just not the right tool for all of this. You can't get performance, you can't do usability, you can't detect product bugs. It goes on and on and on and on and on. You will never invest enough money in type systems to actually have it do what we hope it does. Go for it.
There's a stat about only 5% of program errors being solvable by having a strongly typed environment, or whatever the exact stat was.
Yeah.
How was that measured? Because I feel like there are a number of ways that one could try to model that. But
Fair. And this is one of the things, like, there's lots of empirical studies on type systems and how they're supposed to help developer productivity and correctness and these things. And there's a giant page pointing out that all of them are very, very badly designed, either don't test what they think that they're testing, or actually suggest the opposite, right? When it comes to that particular stat, that was from GitHub. So GitHub did a study where they were looking at errors in CI that they could collect, and which ones they could classify as type errors. And they found that like 5% of them were type errors in dynamically typed languages. They didn't check typed languages for this for obvious reasons. And I think they actually did a decent job. Python was the biggest exemplar in their study.
like, empirically, my intuition would be that in strongly typed languages, you use them insanely.
Yeah.
You do get a lot more than 5% error reduction.
Sure, you just don't in reality. Because it turns out we're smart enough to know that this function with the if statement and the little string concatenation, we're smart enough to know what that does without tests or types. Anyway.
So it seems like you still use languages that have relatively rich type systems. So I'm curious,
Yeah.
at what point do you kind of start drawing the line or a fuzzy boundary where you think that type system features stop becoming useful?
I would say basically everything considered type-level programming. So the processing of things like this, you need a really good justification. All right, that's probably why I bring up Servant. I'm a big fanboy of Servant. But that's an example of a very, very limited use case where this makes sense, right? Almost all other possible use cases do not, right? I wrote an entire application in nothing but type class inductions. And it was just, okay, here's the domain types, and we get the UI, database, everything from that terrible idea.
So you had one point in your slides where you talked about the honesty of types being the cardinality of the values that you're expressing. But
The image.
yeah, sorry. But then earlier you railed against dependent types. How do you reconcile those?
No, I didn't rail against dependent types. I'm pointing out that they're insufficient.
Okay.
They're insufficient to do this, and they're a lot of work.
They are.
They're a ton of work,
That's
right?
true.
So I'm kind of saying that instead of going, we should do all of this work, we should stop ourselves before we invest a week of our time proving something to the compiler that we already know is going to work, and instead go, okay, well, maybe I just allow this to be a little bit dishonest, and then I write a unit test. Any questions?
I think that's it.
We good?
Thank you very much.
All right.